Good day to everyone. My name is Elawarasaan Arasu. I'm from MJIT, UTM. Today, my topic for this presentation is atmospheric dispersion modeling. This presentation contains introduction, physical explanation for the dispersion, the Gaussian model, tall stacks and plumb rise, critical wind speed, other stack design consideration, computer program for dispersion modeling, mobile sources and line source model, and conclusion. As we see for introduction, air dispersion modeling is the mathematical simulation of how air pollutants disperse in the ambient atmosphere. It is performed with computer programs that include algorithms to solve the mathematical equations. The modeling process involves several steps including data collection, model selection, model setup, and model evaluation. The results of the modeling process are typically presented in the form of concentration contours or concentration versus distance plots. Air dispersion modeling has several practical applications: regulatory compliance, environmental impact assessment, emergency response planning. Physical explanation for the dispersion. Air pollutants disperse in the atmosphere due to the following factors. Firstly, diffusion, where the random motion of the molecules due to their thermal energy. Next is advection, the transport of pollutants by the mean flow of air. Next is turbulence, where the regular motion of air caused by obstacles and other factors which can enhance the dispersion of pollutants. When choosing the most appropriate model, the principal issues to consider are the complexity of dispersion, for example, terrain and meteorology effects. Next is the potential scale and significance of potential effects, including the sensitivity of the receiving environment. As we see, the figure below illustrates the types of models typically applied to particle scenarios depending on their scale and complexity. This is the figure for type of model typically applied according to the complexity of the problems. This slide shows the Gaussian model, where the Gaussian model is a widely used approach for air dispersion modeling. It is based on the Gaussian plumb equation, which describes the distribution of pollutant concentration as a function of distance from source. Important subchapters of the Gaussian model include atmospheric stability classes. These classes determine the degree of turbulence in the atmosphere and can influence the dispersion of pollutants. The dependence of concentration on average time, where the average time is the time of the concentration of a pollutant is measured. The dispersion of pollutants can be changed for the average time. In Gaussian models, for a path release, for an idealized instantaneous perfectly spherical release, the concentration of the material in the path has a normal distribution along the two axes perpendicular to wind direction as shown in the figure below. Source clouds for release associated with transportation accidents should be modeled as path release. For Gaussian plumb model, the Gaussian plumb model is the basic for the most air dispersion models, and it is used to predict the concentration of air pollutants downwind of a source. The model is described by the following equation. As we see, C equal to Q over U multiplied by F over Vy 2 pi multiplied by G1 plus G2 plus G3 over G1 plus G2, where C is the concentration of the pollutant, Q is the emission rate of the pollutant, U is the average wind speed, F is the crosswind dispersion parameter. Lambda y is the standard deviation of the crosswind dispersion, and G1, G2 and G3 are the vertical dispersion parameters. For atmospheric stability classes, atmospheric stability classes determine the degree of turbulence in the atmosphere and can influence the dispersion of pollutants. There are three main stability classes. First is unstable, where the atmosphere is more turbulent and the dispersion of pollutants is enhanced. Second is neutral, where the atmosphere is neither stable or nor unstable, and the dispersion of pollutants is less affected by turbulence. The third is stable, where the atmosphere is less turbulent and the dispersion of pollutants is reduced. The dependence of concentration on averaging time. The averaging time is the time over which the concentration of a pollutant is measured. The dispersion of pollutants can change with the averaging time, as the Gaussian-Plum model assumes that the concentration of pollutants is proportional to the square root of the averaging time. When the wind speed is below the critical wind speed, the dispersion of pollutants is limited and their concentration can be higher near the source. As a summary for the Gaussian model, it is an essential tool for air dispersion modeling, and it takes into account important subchapters such as atmospheric stability classes and the dependence of concentration on averaging time. The model is used to predict the concentration of air pollutants downwind of a source and has various practical applications in regulatory compliance, environmental impact assessment, and emergency response planning. As we see for the applications of Gaussian-Plum models, Gaussian-Plum models are widely used, well understood, easy to apply, and until more recently have received international approval. The Gaussian-Plum formula is derived assuming steady-state conditions. That is, the Gaussian-Plum dispersion formula do not depend on time. Although Plum models do not have large meteorological data requirements, the meteorology is a crucial component and good quality data are needed. Gaussian-Plum models are generally applicable when the terrain is not steep or complex. The meteorology may be considered uniform, especially there are few periods of calm or light winds. For tall stacks and plum rise, tall stacks and plum rise are important factors in air dispersion modeling, as they can significantly influence the distribution of pollutants in the atmosphere. Tall stacks can enhance the dispersion of pollutants due to their height and resulting outward movement of air. Plum rise occurs when the upward movement of the stack causes the pollutants to rise, leading to a higher concentration of pollutants at certain distance from the source. For critical wind speed, the critical wind speed is the minimum wind speed required to keep air pollutants suspended in the atmosphere and prevent them from depositing on surfaces. When the wind speed is below the critical wind speed, the dispersion of pollutants is limited and their concentration can be higher near the source. Other stack design considerations that influence atmospheric dispersion include stack height, where the taller stacks can enhance the dispersion of pollutants. Next is exit velocity. The velocity at which the pollutants exit the stack can affect the distribution of pollutants in the atmosphere. Third is exit temperature, where the temperature of the exhaust gas can be influence dispersion of pollutants, and it affects the density and viscosity of stack. For computer program for dispersion modeling, computer programs are used to perform air dispersion modeling, including the AERMOD, CalFAF, and ISC3 models. These programs use input data such as source characteristics, meteorological conditions, and receptor locations to predict the dispersions of pollutants in the atmosphere. Mobile source and line source model. Mobile source such as vehicles and line sources such as highways and railways require different modeling approaches compared to point sources. The modeling of air pollution from mobile and land sources involves appropriate dispersion models to predict the concentration of pollutants along the path of the sources. For conclusion, air dispersion modeling is an essential tool for predicting the concentration and distribution of air pollutants in the atmosphere. The Gaussian model, torque stacks, plumb rise, critical wind speed, and other stock design considerations are important aspects of air dispersion modeling. Computer programs and models are used to perform air dispersion modeling, and their results have practical application in regulatory compliance, environmental impact assessment, and emergency response planning. That's all from me, and thank you so much.